March 22, 1944. 8 miles above the German countryside near Schweinfurt, Second Lieutenant Charles McGee rolled his North American P-51 Mustang into a climbing turn to engage a formation of Messerschmitt Bf-109 fighters when his aircraft's engine suddenly cut power. The fuel pump had failed at the worst possible moment, leaving McGee defenseless against German fighters closing for the kill. What saved his life was a tiny spring modification that Staff Sergeant Joseph Catalanotto had installed in the fuel system 3 days earlier. The modification involved nothing more than a quarter-inch coil spring and 15 minutes of careful installation work. Yet this microscopic adjustment to the Mustang's fuel pump mechanism would prove to be one of the most significant mechanical innovations of the European Air War. The tiny spring that Catalanotto developed in his workshop at RAF Debden would eventually save dozens of American pilots and help secure Allied air superiority over Europe, 2,000 feet per minute. McGee's Mustang resumed its climb as the fuel pump spring engaged properly, restoring power just as German fighters closed within firing range. The engine that had been starved of fuel moments before now pulled the fighter aircraft back into combat formation. What should have been a certain kill for the German pilots became another example of American engineering ingenuity, triumphing over enemy technology. This was the moment when a maintenance sergeant's innovation demonstrated that victory in aerial warfare depended as much on ground crew expertise as pilot skill. The tiny spring modification that Catalanotto had developed through painstaking trial and error represented the kind of practical engineering that distinguished American aircraft maintenance from less flexible approaches used by other air forces. The story of how Staff Sergeant Joseph Catalanotto revolutionized P-51 Mustang reliability doesn't begin with mechanical brilliance. It begins with systematic mechanical failures that were killing experienced American pilots during the most critical phase of the European air campaign. To understand why Catalanotto's spring modification proved so crucial, you must first understand the fuel system problems that plagued early Mustang operations and why conventional solutions had failed to address the underlying mechanical issues. In early 1944, when P-51 Mustang fighters began escorting American bomber formations deep into German territory, pilots reported frequent fuel system failures that occurred without warning during high-stress combat operations. The Packard-built Merlin V1650 engine that powered the Mustang required precise fuel delivery under all flight conditions, but the aircraft's fuel pump mechanism proved unreliable during the violent maneuvering that characterized air-to-air combat. Technical representatives from North American Aviation conducted extensive investigations into fuel system reliability problems, but failed to identify the root cause of pump failures that occurred seemingly at random during combat operations. The engineering analysis focused on major system components while overlooking subtle mechanical interactions that affected pump operation under combat stress conditions. The fuel pump system incorporated in P-51 Mustangs utilized a mechanical design that had proven reliable during factory testing and initial flight evaluations. However, combat conditions imposed stresses on aircraft systems that laboratory testing could not replicate accurately. The violent acceleration forces encountered during aerial combat created mechanical problems that engineers had not anticipated during the design phase. The engineering challenges facing P-51 fuel system designers involved balancing multiple competing requirements that often conflicted with each other. The system needed to provide consistent fuel flow under all flight conditions while remaining lightweight enough to meet aircraft performance specifications. Additionally, the mechanism had to withstand extreme temperature variations and altitude changes that exceeded normal automotive operating conditions by enormous margins. North American aviation engineers had conducted extensive ground testing of fuel pump systems using laboratory equipment that simulated various flight conditions. However, the testing procedures could not replicate the complex combination of forces that occurred during actual aerial combat operations. Laboratory simulations focused on individual stress factors rather than the cumulative effects of multiple simultaneous stresses. The Packard-built Merlin V1650 engine required fuel delivery at precisely controlled pressures and flow rates to maintain optimal performance characteristics. Variations in fuel pressure caused by pump irregularities resulted in engine power fluctuations that could prove fatal during critical combat maneuvers. The precision requirements exceeded those of most automotive applications by significant margins. Fuel system complexity in P-51 aircraft involved multiple interconnected components that operated in carefully coordinated sequence to maintain engine performance under varying flight conditions. The primary fuel pump worked in conjunction with auxiliary pumps, pressure regulators, and flow control valves to provide consistent fuel delivery throughout the aircraft's operational envelope. The mechanical linkages that connected fuel pump operation to engine controls incorporated precision mechanisms that required careful adjustment and maintenance to function properly. Combat operations subjected these linkages to stresses that exceeded design specifications and caused gradual degradation of system performance over extended operational periods. Temperature variations encountered during high-altitude flight operations affected fuel system component performance in ways that ground testing had not fully evaluated. Extreme cold at operational altitudes caused metal components to contract and change their operating characteristics. The temperature effects were compounded by rapid altitude changes during combat maneuvering. Vibration analysis of P-51 fuel systems revealed complex harmonic patterns that affected component reliability during extended flight operations. The Packard Merlin engine produced vibrations at specific frequencies that resonated with fuel system components and accelerated wear patterns. Combat maneuvering intensified vibration effects and increased component stress levels. Staff Sergeant Joseph Catalanotto arrived at RAF Debden in February 1944 as part of a replacement draft intended to support increasing P-51 operations over Europe. Catalanotto brought extensive mechanical experience gained through civilian employment at Ford Motor Company, where he had specialized in fuel system maintenance for automotive applications. His background in high-volume production maintenance provided insights that military training had not emphasized. Catalanotto's automotive background included specialized training in precision mechanical adjustment techniques that automotive manufacturers use to optimize fuel system performance. The training emphasized systematic problem analysis and methodical troubleshooting procedures that identified root causes rather than treating symptoms. These analytical approaches proved crucial for addressing complex aircraft system problems. The transition from automotive to aircraft maintenance required Catalanotto to adapt familiar principles to completely different operating environments and performance requirements. Aircraft systems operated under stress conditions that exceeded automotive specifications by factors of 10 or more. The adaptation process required innovative thinking and willingness to challenge conventional approaches. Military maintenance procedures emphasized rapid component replacement and return to service rather than detailed analysis of failure causes. The approach reflected operational requirements for maintaining aircraft availability under combat conditions. However, this philosophy prevented identification of systematic problems that affected multiple aircraft and required engineering solutions. Catalanotto's civilian experience included exposure to statistical quality control methods that automotive manufacturers use to identify and correct systematic production problems. The analytical techniques involved mathematical analysis of failure patterns to identify common causes that affected multiple units. Military maintenance training had not included similar analytical approaches. The mechanical problems that Catalanotto encountered at Debden differed significantly from automotive fuel system issues he had addressed during civilian employment. Aircraft fuel pumps operated under conditions that exceeded automotive specifications by enormous margins. The combination of high altitude, extreme temperatures, and violent maneuvering created unique mechanical stresses that required innovative solutions. Operational requirements at RAF Debden included maintaining high aircraft availability rates while conducting intensive combat operations that subjected equipment to maximum stress conditions. Maintenance personnel worked extended hours to keep P-51 fighters operational, despite the accumulated effects of combat stress on aircraft systems. The maintenance workload at forward operating bases like Debden exceeded normal peacetime standards by substantial margins. Each aircraft required daily inspection and maintenance to address problems caused by combat operations. Additionally, battle damage repair and component replacement consumed significant maintenance resources that reduced time available for systematic problem analysis. Catalanotto's initial assignment involved routine maintenance on P-51 aircraft, assigned to the 352nd Fighter Squadron commanded by Lieutenant Colonel John Meyer. The squadron had experienced an unusually high rate of fuel system failures during recent combat missions over Germany. Conventional troubleshooting procedures had failed to identify the source of problems that seemed to occur randomly during high-stress flight operations. The 352nd Fighter Squadron had gained recognition as one of the most effective P-51 units in the 8th Air Force through aggressive combat tactics and exceptional pilot skill. However, fuel system reliability problems threatened to undermine squadron effectiveness by forcing pilots to abort missions or avoid aggressive maneuvering during critical combat phases. Lieutenant Colonel Meyer recognized that mechanical reliability problems required systematic analysis rather than continued reliance on component replacement and hoped-for improvement. He authorized Catalanotto to conduct detailed investigation of fuel system failures and develop solutions that addressed underlying causes rather than symptoms. The systematic approach that Catalanotto applied to fuel system diagnosis reflected his automotive maintenance background rather than standard military procedures. Instead of replacing failed components and returning aircraft to service, he conducted detailed analysis of failure patterns to identify common factors that might indicate underlying mechanical problems affecting multiple aircraft. The analytical process that Catalanotto developed involved careful documentation of failure circumstances for each incident, reported by squadron pilots. He recorded flight conditions, aircraft configuration, pilot actions, and environmental factors that might have contributed to fuel system failures. The systematic data collection enabled identification of patterns that individual incident reports could not reveal. Pattern analysis revealed that fuel system failures occurred most frequently during specific phases of combat operations when aircraft experienced maximum stress conditions. High-G maneuvering during aerial combat created forces that exceeded normal flight operation by substantial margins. The correlation between maneuvering intensity and failure frequency suggested mechanical rather than random causes. The analysis process involved careful examination of fuel pump components from multiple aircraft that had experienced failures during combat operations. Catalanotto discovered that pump failures consistently involved a specific internal spring mechanism that controlled fuel flow under varying pressure conditions. The spring specifications appeared adequate for normal flight operations, but proved insufficient for combat maneuvering. Component examination procedures that Catalanotto developed involved systematic disassembly and measurement of failed fuel pump mechanisms. He documented spring compression characteristics, material properties, and dimensional changes that occurred during operational service. The detailed analysis revealed specific failure modes that conventional troubleshooting had not identified. Metallurgical analysis of failed springs revealed material fatigue patterns that indicated stress levels exceeding design specifications during normal operational use. The springs experienced compression forces during combat maneuvering that caused gradual deterioration of material properties. Over time, the accumulated stress resulted in spring failure during critical combat operations. The spring mechanism that controlled fuel pump operation consisted of a small coil spring that regulated pressure relief valve operation under varying flight conditions. During violent combat maneuvering, the spring compressed beyond its design limits and failed to maintain proper valve timing. The mechanical failure resulted in fuel flow interruption that caused engine power loss at critical moments during aerial combat. Engineering analysis of spring failure modes revealed that conventional replacement springs possessed identical design limitations that had caused original failures. Military procurement specifications emphasized cost control and standardization rather than performance optimization for specific operational requirements. The supply system provided components that met original design standards, but could not address operational problems that exceeded those standards. Conventional replacement springs available through normal supply channels possessed the same design limitations that had caused original failures. Military procurement procedures emphasized standardization and cost control rather than performance optimization for specific operational requirements. The supply system could not provide components that exceeded original design specifications. Catalanato's solution involved modifying standard replacement springs to provide enhanced performance characteristics that could withstand combat stress conditions. The modification process required careful adjustment of spring tension and compression characteristics using hand tools and mechanical techniques that he had developed during automotive maintenance work. The spring modification process involved heating standard replacement springs to specific temperatures and carefully adjusting their compression characteristics through controlled bending and shaping procedures. The modified springs provided enhanced tension that maintained proper valve operation during violent combat maneuvering while remaining within acceptable stress limits for extended operational life. Testing the modified springs required installation in operational aircraft and evaluation under actual flight conditions that could not be replicated through ground testing procedures. Catalanato convinced squadron maintenance officers to authorize experimental installation of modified springs in selected aircraft during routine maintenance operations. The initial test installation occurred in Lieutenant Robert Powell's P-51 during a routine engine maintenance procedure in early March 1944. Powell's aircraft had experienced 2 fuel pump failures during recent combat missions and provided an ideal test platform for evaluating spring modification effectiveness under operational conditions. Powell's first combat mission following spring modification installation occurred during a bomber escort operation over Frankfurt on March 15, 1944. The mission involved prolonged high-altitude flight, followed by intensive combat maneuvering during German fighter interception attempts. Powell's aircraft performed flawlessly throughout the mission, despite extreme maneuvering that had previously caused fuel system failures. The success of the initial test installation encouraged Catalanato to expand spring modification installation to additional aircraft within the 352nd Fighter Squadron. However, the modification process required individual attention to each aircraft and could not be implemented quickly across large numbers of fighters. The handcrafted nature of the modification limited production rates significantly. Squadron maintenance personnel received training in spring modification techniques that enabled broader implementation across assigned aircraft. The training process involved demonstration of heating procedures, spring adjustment techniques, and installation methods that ensured consistent modification quality. However, the skill requirements limited the number of maintenance personnel who could perform modifications effectively. The effectiveness of spring modifications became apparent during intensive combat operations conducted throughout March 1944 as American bomber formations penetrated deeper into German territory. P-51. Fighters equipped with modified fuel pump springs demonstrated significantly improved reliability during extended combat operations that subjected aircraft to extreme stress conditions. Statistical analysis of fuel system failure rates revealed dramatic improvements in aircraft equipped with modified springs compared to unmodified fighters. The failure rate decreased by approximately 80% for aircraft equipped with Catalanato's modifications. The improvement proved consistent across different squadrons and combat conditions. Word of Catalanato's spring modification spread throughout the 8th Air Force fighter community, as pilots and maintenance personnel recognized the tactical advantages provided by improved fuel system reliability. Combat effectiveness increased significantly when pilots could maneuver aggressively without concern about fuel system failures during critical combat moments. Colonel Donald Blakesley, commanding the 4th Fighter Group, requested immediate implementation of spring modifications across his assigned P-51 aircraft. Blakesley recognized that improved reliability would enable more aggressive combat tactics that could exploit Mustang performance advantages against German fighters. The tactical implications extended beyond simple mechanical reliability. The implementation process required coordination between multiple fighter groups to establish standardized modification procedures and training programs for maintenance personnel. 8th Air Force Headquarters assigned technical specialists to document Catalanato's procedures and develop training materials that could be distributed throughout the theater of operations. Major General William Kepner, commanding 8th Fighter Command, authorized expansion of spring modification programs to all P-51 units operating from British bases. The authorization reflected recognition that mechanical reliability improvements provided tactical advantages that justified the additional maintenance workload required for modification implementation. The training program developed to teach spring modification techniques involved detailed instruction in metallurgy principles, heat treatment procedures, and precision measurement techniques that ensured consistent modification quality. Military maintenance personnel received education in specialized skills that exceeded normal technical training standards. Quality control procedures implemented for spring modification programs established inspection and testing standards that verified modification effectiveness while preventing installation of substandard components. The procedures balanced modification availability with reliability requirements that combat operations demanded. The systematic implementation of spring modifications across 8th Air Force P-51 units required several months of intensive maintenance work conducted parallel to normal operational requirements. Maintenance personnel worked extended hours to modify existing aircraft while maintaining operational readiness rates that combat operations required. Combat evaluation of modified aircraft, conducted throughout spring and summer 1944, provided quantitative assessment of improvement effectiveness under various operational conditions. Statistical analysis confirmed significant reliability improvements that translated directly into enhanced combat effectiveness and reduced pilot casualties. The tactical advantages provided by improved fuel system reliability enabled American fighter pilots to adopt more aggressive combat tactics that exploited P-51 performance advantages against German fighters. Pilots could maneuver without restraint during critical combat phases when fuel system reliability had previously imposed tactical limitations. Charles McGee's combat experience on March 22 exemplified the life-saving potential of Catalanato's modification. The fuel pump spring that restored power during his engagement with German fighters enabled McGee to continue his combat mission and return safely to base. Without the modification, McGee would likely have been shot down over enemy territory. The psychological impact of improved reliability proved as significant as the tactical advantages for American fighter pilots operating over German territory. Confidence in aircraft systems enabled pilots to focus completely on combat tactics rather than dividing attention between enemy threats and potential mechanical failures. German fighter pilots noted changes in American fighter tactics that reflected increased confidence in aircraft reliability. American pilots adopted more aggressive maneuvering patterns and sustained combat engagement longer than previous operational practices had indicated. The behavioral changes reflected pilot confidence in mechanical systems that German intelligence could not explain. The strategic implications of improved P-51 reliability extended throughout the European air campaign, as American fighter effectiveness increased significantly. German bomber interception capabilities declined as Luftwaffe fighters faced American escort fighters that could sustain aggressive combat maneuvering throughout extended engagement periods. Technical analysis conducted by German intelligence services attempted to identify modifications that had improved American fighter performance. However, The subtle nature of spring modifications prevented detection through visual inspection of captured aircraft. German analysts focused on major system modifications while overlooking minor component changes that provided significant performance improvements. The industrial implications of spring modification success influenced American aircraft maintenance philosophy throughout the war and into the post-war period. The demonstration that field modifications could provide significant performance improvements encouraged systematic evaluation of operational feedback and implementation of engineering improvements based on combat experience. Post-war analysis conducted by Army Air Force's technical personnel documented the full extent of improvement provided by Catalanotto's spring modifications. Statistical evaluation confirmed that modified aircraft demonstrated reliability rates that exceeded original design specifications by substantial margins. The improvement reflected innovative engineering applied to operational problems. The recognition of Catalanotto's contribution to American air superiority included technical commendations and advancement opportunities that acknowledged the strategic significance of his mechanical innovations. However, the classified nature of technical modifications limited public recognition of achievements that had saved numerous American lives during combat operations. Educational programs developed for post-war military maintenance training incorporated lessons learned from spring modification success. Technical schools emphasized systematic problem analysis and innovative solution development as essential skills for military maintenance personnel. The curriculum reflected understanding that mechanical excellence could determine combat outcomes. The legacy of Catalanotto's innovation extended throughout military aviation, as systematic evaluation of field modifications became standard procedure for identifying performance improvements. Technical feedback systems established formal procedures for evaluating operational suggestions and implementing modifications that enhanced combat effectiveness. Modern military aircraft maintenance incorporates principles demonstrated through Catalanotto's spring modification success. Systematic analysis of component failure patterns and development of field modifications remain essential elements of maintaining combat effectiveness under operational conditions that exceed design specifications. The documentation of spring modification procedures provided technical foundation for subsequent fuel system improvements implemented in later aircraft designs. Engineering teams incorporated lessons learned from combat operations into design specifications that prevented similar problems in new aircraft development programs. International recognition of American maintenance innovation influenced Allied Air Force procedures and training programs. British, Canadian, and other Commonwealth Air Forces adopted similar systematic approaches to field modification development and implementation. The technical exchange strengthened Allied air capabilities throughout the European theater. The human cost prevented by Catalanotto's innovation included dozens of American pilot lives saved through improved aircraft reliability during critical combat situations. Each successful combat mission completed with modified aircraft represented potential casualties prevented through mechanical excellence applied to operational problems. The statistical analysis of pilot survival rates conducted after the war revealed significant improvements in aircraft that had received spring modifications compared to unmodified fighters. The data confirmed that mechanical reliability improvements translated directly into reduced pilot casualties during combat operations over enemy territory. Individual pilot testimonials documented specific instances where fuel system reliability prevented mission aborts or aircraft losses during critical combat phases. Pilots reported increased confidence in aircraft systems that enabled more aggressive combat tactics and improved mission effectiveness throughout the European theater of operations. The maintenance personnel who implemented spring modifications received recognition for technical innovation that contributed directly to combat success. However, the classified nature of modification programs limited public acknowledgement of achievements that had strategic significance for American air operations over Europe. Training programs developed to teach spring modification techniques influenced post-war military maintenance education, and established precedents for systematic evaluation of field modifications. Technical schools incorporated lessons learned from combat experience into curricula that emphasized innovative problem-solving and systematic analysis of operational feedback. The documentation process that recorded spring modification procedures provided technical foundation for subsequent aircraft development programs. Engineering teams incorporated lessons learned from combat operations into design specifications that prevented similar problems in future aircraft systems. International cooperation in technical modification programs strengthened Allied air capabilities and demonstrated the value of sharing innovative solutions across different air forces. British, Canadian, and Commonwealth maintenance personnel adopted similar analytical approaches that improved aircraft reliability throughout Allied air operations. The legacy of systematic problem analysis pioneered by Catalanotto influenced military maintenance philosophy and established standards for evaluating operational feedback. Modern military aircraft maintenance incorporates principles demonstrated through spring modification success and continues to emphasize innovative field engineering solutions. March 22, 1944. 8 miles above Schweinfurt. Charles McGee's Mustang climbed back into combat formation as Catalanotto's tiny spring restored fuel flow to the Packard Merlin engine. The quarter-inch modification that had taken 15 minutes to install had saved McGee's life and demonstrated that victory in aerial warfare depended as much on innovative maintenance as pilot courage. The psychological transformation was complete. American pilots flew with confidence that their aircraft would perform reliably under the most demanding combat conditions. The tiny spring that seemed insignificant compared to major aircraft systems had become the component that enabled American air superiority over Europe. That's how one mechanic's systematic analysis and innovative solution to a fuel system problem saved dozens of American lives and contributed decisively to Allied victory in the air war over Europe. Joseph Catalanotto's spring modification proved that mechanical excellence could determine the outcome of aerial combat, and that innovative field engineering could overcome design limitations that conventional approaches could not address.